Now it's time to move on from the last couple of presentations which focused on inference and inferential stats in a theoretical way to start looking at some of the practical ways that we can start doing some of these so-called real stats models and move on from the descriptive nature of the analyses we've done previously. So far we've looked at these descriptive quantitative methods. Back when we've looked at things like frequency tables and looking at central tendency and dispersion and doing graphs. Next we have to think about the sort of actual tests of what we're interested in. We have three different kinds of options available to us, and we're going to look at these over the next three presentations, and then there's a final presentation which considers going beyond some of the t-test categorical continuous in the last bullet point there into some slightly more complex things as well. Categorical variables, when we have two of those, we can do what's called the crosstabs. When we have two continuous variables, we can do what's called correlations, both things that we've touched on briefly in some of the previous presentations. And then if we've got a combination of categorical and continuous, we can do t-tests, something we spoke about in the last presentation to do with the RCT. But then we can also build on these and become much more complex too. For the purposes of the teaching, we're going to focus on the crosstabs in this presentation, correlations in the next, and then t-tests, and then thinking about how we can expand these. But the expansion of these kind of models gets more and more complex, but the foundations are the same. It's just kind of adding in some more complexity because in the real world our data sometimes are more complex than we can just run some of the more simple statistical models with. The two main variables in a study are the independent and dependent variables. Independent variables stand alone and they aren't changed by the other variables that you're trying to measure, hence why they're called independent. Dependent variables, on the other hand, depend on the other factor. And these kind of terms, the terminology is something you need to learn because you'll see it in SPSS software, you'll see it in people and how they write about some of their stats models, you'll see it in textbooks. Sometimes we might call some of these factors the predictors, so the independent variables and the dependent variables as more like outcomes. But it's important to make sure that you're aware of what these terms are because if you come across them, you'll know what we're looking at. And so what we would typically say when we're describing these different variables is that the independent variable is associated with a change in the dependent variable, but it isn't possible that the dependent variable could cause a change in an independent variable. Now let's look at what we mean by that in a bit more detail. For example, age is associated with a change in cholesterol, but it isn't possible that cholesterol could cause a change in age. Sex is associated with a change in cholesterol, but it isn't possible that cholesterol could cause a change in someone's sex. So the independent variables, things like age and sex, what we're kind of interested in using as, predictors potentially. And then we have cholesterol here, which is our dependent variable, the kind of outcome of interest that we're looking to measure. With that kind of information, knowing what our dependent and independent variables is, obviously the next stage is understanding, well, what kind of construct, what type of data do we have within those variables, and that is important for then determining the types of tests that we can run. If we want to describe a single categorical variable, we use frequency tables, something we did back in one of the early exercises, exercise 1, when we created frequency tables by looking at individual variables in our data set. If we want to describe the relationship between two categorical variables, we use what's called a table, known as a cross-tabulation or a crosstab. This is also sometimes called a two-way table or a two-way crosstab or a contingency table. Just in case you come across these terms in your reading, they're basically all the exact same thing. In a crosstab, the categories of one variable determine the rows of our table, or crosstab table or contingency table, and the categories of the other variable determine the columns. The cells of the table contain the number of times a particular combination of these categories occur. Now, it doesn't really matter which way you have the rows or the columns, but the best way to think about it is which one relates to the other, which one is the independent variable, which one is your dependent variable. So in this case, we have a sample where we've asked people who are a group of men and a group of women whether they drink alcohol, and they've answered yes or no. In terms of independent and dependent variables, here our independent variable is likely gender, sex, male versus female. because that could potentially lead to a change in how people answer the question about do they drink alcohol. But whether people drink alcohol or not does then not create someone's sex. But it doesn't really matter too much in a crosstab because you've just got these two categorical variables, which way you put them in. It's just to make sure you understand which one you're thinking of theoretically as your dependent variable and which one you're thinking of as your independent variable. In this example, you can see that we've got a total of 91 people in our sample. If we look across the rows, so we start off with men, the male gender, we have 13 individuals, 13 men said they did not drink alcohol, 33 said they did drink alcohol, giving a total of 46 men in the sample. For the women in the sample, 13 said they did not drink, whereas 32 said they did drink, so giving us 45 women in our sample. We can then look down the columns instead, who said that they drank alcohol, whether they said, those that said they didn't drink alcohol, we had 13 males and 13 females. Those that said they did drink alcohol, we have 33 males and 32 females. So in total we had 26 people across our sample, male and female, that said they didn't drink alcohol, and 65 said that they did. So from this kind of crosstab, we can look at that and get some information about do men drink more than women in our sample. And from this one, we can see that there's not any difference because essentially they've got the exact same numbers there. You've got the same number of men versus women with only one individual more in our male sample than in our female sample, but they've essentially answered the question in the exact same way, with 13 out of those 46 saying that they do not drink alcohol. Now the crosstab is still basically a descriptive table. However, we can test if there are patterns in the data, and this test is known as a chi-square. So when we look to the data, it's pretty clear here that there's not going to be any effect going on because the numbers are almost identical, but we can still run the test, the chi-square, to see if that is actually the case. Obviously, most examples we might have are not going to be as obvious as this. The chi-square test of independence, to give it its full name, determines whether there's an association between categorical variables. It's a non-parametric test, and you're testing the null hypothesis that variable 1, gender, sex in that example, is not associated with or is independent of variable 2, alcohol, whether you drink it or not. So your p-value that comes back will allow you to either accept or reject the null hypothesis that there's no relationship between sex and drinking alcohol. Now it's time for you to go and do exercise 5, which is running a crosstab. So you're going to do essentially what we've done in those examples. You're going to create your crosstab table, and then you're going to run your chi-square analysis as well to get an answer. So if we were to look back at the previous example, when we run our chi-square, I don't have the exact numbers in front of me, but the chi-square p-value here is going to be really, really high because we're not going to feel confident in being able to reject the null hypothesis that there's no relationship between being male or female and drinking alcohol. There's no pattern going on here. So there's no relationship between sex and alcohol. So we won't be able to reject the null hypothesis. The p-value is probably pretty close to 1, almost as high as as high as you can get it. It's probably about 0.9 something. As opposed to if there was differences going on, remember we would have a really low p-value and we'd feel more confident about rejecting the null hypothesis. So have a look at exercise 5, work your way through it, and we'll catch up later on with the Q&A if you've got any questions related to it. And next we're going to move on to look at correlations and how we run correlations in SPSS2.